Or you might die after 11 more terms. Or you might die after 158 more terms. Or, I'm going to write question mark here, but I will talk about this case. Like, question mark means I can describe what's going on, but I don't know if it dies. So, it has a regular form, regular looking form, hard to analyze. And so I said 4 possible behaviors. There's a 5th thing as well. I said mod 5. And these correspond to like 4 of something mod 5. But the 5th case is you get a quasi-polynomial for a while, and then you have to, that's what the certain point is. At a certain point, you just get another quasi-polynomial until you get to a certain other point, and then you check these things again. So you might also have to keep going and get to another certain point. And that might happen arbitrarily many times. But what ends up happening in this first block, so the n plus something, you end up with a quasi-polynomial of period 5 that you eventually land in, and you're there until about 2n, around the index 2n, which is where you have to make your first decision. And if n is congruent to 0 mod 5, you land in this case. If n is congruent to 1 mod 5, you land in this case. If n is congruent to 2 mod 5, you have to keep going. If n is congruent to 3 mod 5, you're here. And if n is congruent to 4 mod 5, you're here.
Is this the case where for strong death, or is this for all cases?
This is strong death. I mean, this is the same exact sequence over there. So we already analyzed weak death. So these sequences, we're assuming that Q of n is 0 for n less than or equal to 0. So that's really important because we're going to have terms in here that are really big. And the point is that those terms don't actually matter really. They just cause things to zero out.
But there are other cases when it lives, right? So,
Well, what I mean by like 158 more terms is after you get to this point, the 157th and the 158th term after that point are both big. Which means, or the 156th and 157th term are both big. That means the 158th term is 0, which means it then dies. And all 3 of these cases, that happens. This case, I don't think that happens. I have a conjecture that it does not happen.
N is a symbol denoting a very big number.
Yes.
So it's relative to n, it's a big.
Yes, they're big relative to n. Except these all work if n is greater than or equal to 35.
Oh, so that's the one for.
As long as n is greater than or equal to 35, this all works, except for this guy. This case requires n to be at least 118.
Oh, so n is a specific number.
So basically, the way we do this is we assume n is some really big symbol.
That's a sufficiently large number.
Yeah, sufficiently large number. And then we just, over the course of the algorithm, figure out what sufficiently large meant. Because we have all these assumptions that we're making. We can write all those assumptions down, solve a linear program, and figure out what n actually had to be. So we start off with n is just a huge symbol. But we can look at what our algorithm did and say, oh, all we needed was n to be this big or bigger. So I want to talk about that 4th case there, because that 4th case is really strange and really interesting in my opinion. So here's a picture of that 4th case.
Nathan, I have to leave. I have notes.
Okay. Thank you for coming. So this is not exactly that case, but this is the eventual behavior in that case. This is one sequence. This is not 4 sequences. This is one sequence. But you notice it splits into like 2 things down here. This big thing that seems to dominate everything, and there's also a constant piece down here.
Those are like the zeros.
Here. They're not 0. If they were 0, the thing would have died.
Okay.
They're actually 4. So the thing I'm going to write down, like at first when I was looking at this thing, like why is my program not guessing a quasi-polynomial for this? But then I looked more carefully and realized, wait, it's not a quasi-polynomial. It's 4 every fifth term. So like it has constants at regular intervals. But the rest of the terms are not polynomials. So like empirically, these both grow linearly, and this thing is going to grow like n to like the 1.29 just based on an empirical estimate. But the I can't prove anything. Yeah.
What is the end value for this particular sequence?
I mean, this isn't it dead. I just cut it off at like 8,000 or something.
No. What is the
This isn't, as I said, this isn't a specific one. This is just what the eventual behavior looks like.
Ah.
So if we define so R of 1 is equal to 1, R of 2 is equal to 2, and then R of n is R of n minus R of n minus 1 plus S of n minus 1 for n greater than equal to 3. Well, of course, what do I need? But I need to define S. S of 0 is 1, S of 1 is 1, S of n is S of n minus R of n plus S of n minus R of n minus 1 for n greater than equal to 2. And T of 0 is 1, and then T of n is T of n minus R of n plus T of n minus S of n for n greater than equal to 1. So this is 3 nested recurrences. These ones depend on each other. This one just depends on these two. But you end up with a solution to the Hofstadter recurrence. So I'll write down the solution to the Hofstadter recurrence, this one, and then I'll explain how it starts appearing in these other solutions. So, but the solution there is, so that's this A272610 sequence is 5, 9, 4, 6, 5, 5, 18, 4, 5, 10, 10, 18, 4, 10, 15, 10, 27. So in general, this 6 only needs to be greater than or equal to 6. It can be anything as long as it's at least a 6. And this 9 can be a big symbol. It can be whatever as long as it's at least 9. And then this is, I believe, 5 times R1. This is 5 times S1. And this is n times T1. This is always 4. And then this is 5 times R1. And then this is 5 times R2. And so on. So the R, S, T, 4, R. And that just keeps repeating. And as long as these R, S, and T sequences never, well, the R and S sequences, if they weakly die, I feel like this would break down. But I don't think they weakly die. So again, here's what the R and S sequences look like. So the R sequence is empirically going to be about n over 2. The S sequence is going to empirically be about n over 4. And that seems to last for a while. But as long as these don't die, this case doesn't die at all. Well, actually, I guess it doesn't die strongly. It keeps, because the T sequence grows faster than N, so it's got to die weakly. All right, so I'm running low on time, so rather than write more things down, I'm just going to show more pictures. So I guess first I'll rant a little bit about what the peak going thing is. So when n is congruent to 2 mod 5, then you have to look mod 25. And of course there are 5 possible values that are congruent to 2 mod 5. So it could be 2 mod 25, it could be 7, it could be 12, 17, or 22. And it turns out that each one of those corresponds to one of these cases where if it's 17 mod 25, you have to go even deeper. And this just keeps on going. So this is 2 mod 5, 17 mod 25, 117 mod 125, 492 mod 625, 1742 mod 3125. And first of all, does anyone see a pattern? Because I don't. But then,
So how far can you go? It's not a sequence.
I mean, I can keep going, but the problem is, all 5 of them mod 5 to the 6th, you have to keep going. So here it was just one case for everything, but now all of them are keep going. And then below this one, and below the first one here, and below the 4th one, they're all this nonsense. Below the 5th one, they all die after 11 more terms. Below the 2nd and 3rd one, they all tell you to keep going. And at this point, I just have no idea what's going on. I have a way of predicting, like an iterative algorithm to predict what's going to happen. And I'll just show you on here. This is eventually going to be a paper about this. How I have this sequence, these AIs and these BIs, and BI has like a 110 in it, and n mod 5 appears a bunch of times. That's B1. And then you have a recursive definition where these things are all multiplied by each other. And if you just try to write these things down, they're all polynomials, but they all depend really intricately on the congruence of n mod a bunch of powers of 5. And in my mind, it kind of looks like a pseudo-random number generator. So I have that. So these are probably pseudo-random numbers. So I have no clue what's actually going on here. But in each particular case, I can run the algorithm and see what's going to happen. So that's these Hofstadter recurrence 1 through n guys. So now I'm just going to show pictures of other things. So in addition to the Hofstadter recurrence, you might consider, the natural generalization of the Hofstadter recurrence. That's probably if you just add more I raised the recurrence. Is if you add more terms to the recurrence. So like Hofstadter was q of n minus q of n is equal to q of n minus 1 plus q of n minus q of n minus 2. You can just add more to that. You can just keep going. So the first thing to look at is what if you just add one more term. So now we have an n minus 3 term. And turns out if you give that thing the initial condition 1, 1, 1, which seems like the natural generalization of Hofstadter is 1, 1, it dies after like 800 terms or something. But if you give it an initial condition 1 through symbolic n, you enter and you look at if you're looking for strong death, they all die. In the same way like that, you could write down a theorem like that, and they all die in this case after n plus 24 terms. So the things on that board, there would only be 24 of them instead of 28, and then you'd get one that's 2n plus something, and the thing would die weakly. But if you want it to die strongly, well, there's good news. I got good news for you. You don't have any of this crazy stuff. The bad news is now it's mod 7 that matters. So, but the theorem is, I'll just read you the theorem, I'm not going to write it down. If n is congruent to 0 mod 7 and it's at least 196, it dies after 2n plus 27 terms. So like between n and 2n, you enter a quasi-polynomial with 7 pieces. So like over here, you enter a quasi-polynomial with 5 pieces. So this one enters one with 7. So then if n is congruent to 1 mod 7 and ends at least 2087, it dies after 2n plus 54 terms, or 2n plus 254 terms. And then there's a bunch more cases, the most intriguing of which is if n is congruent to 5 mod 7, and n is greater than or equal to 32,478, then it dies after 2n plus 4,547 more terms. And that's tight. So if you subtract 7 from that, it still dies, but it dies after more terms. It's sort of like the 14 through 20 case, where it still dies, but it takes a little bit longer. And this is actually first. This is the this is actually back to this. So this is the case of n equals 42 back to the Hofstadter recurrence, and 42 is 17 mod 25. So you have to keep going twice. But then you end up in this RST mayhem, and you can see here, this is the T sequence times n. So 42 times the T sequence is right here, and then you can't really see the other things that are happening. But you might say, oh, I promised you that there would be three cases here. It looks like there's just this line. But then you look at the scale on this axis and you go, oh wow, this is a really steep line. But you also are thinking I lied to you because I told you that this line, I told you there would be three blocks, because there's the first block from n over here, and then there's the block from it being 2 mod 5, and there's the block from it being 17 mod 25. Turns out there are 3 blocks here, it's just the first 2 are in here, and this is the third block, because the blocks are like, each one's length is about the square of the previous one's length. So it grows really fast. So to see that, well here, this is a log plot of the previous plot, so you can still see the RST stuff, but just still all of this is that third block. So now this is both axes log. You can see that there are actually 3 things going on. This is the first block, this is the second block, this is the third block, and then here's this RST behavior. So this is what I promised you with this 32,478. This is the first 64,964 terms of this sequence. That's not quite how long I said it would last, because I said it would last for 2n plus 4,547 terms. And yes, by the way, that point up there is not a typo. That actually is in the sequence. But so here you can just see this is the initial condition. And then this, after there's 66 mayhem terms in the middle, and then there's a quasi-polynomial with 7 pieces. 2 of the pieces are basically on top of each other right here. Then this is if you go out a few more terms. You can see there's some regular chaos going on here. Like you can see patterns. But then it dies, and those terms get huge before it dies. So this is the first plot I generated, and it's like you can't even see anything except those last terms. So like here's a log plot of the entire sequence, and you could just see this thing taking off at the very end. So this is the whole sequence. So now, why stop at 3? We can keep going. And it turns out, if you keep going, you can handle all the rest with a single theorem. They all follow the same kind of behavior, which is 1 through n, quasi-polynomial, where all the pieces are linear, and there's a specific number of them. And I believe that number is the number of terms in the recurrence plus 1. And then after that, chaos. This is the 4-term Hofstadter recurrence. 1 through 3,000 is the initial condition. Again, this is actually here. And there are either 4 or 5 things interleaved here, but then once that stops, it doesn't seem to die, but I have no clue what's going on. And then here's the 5-term recurrence, same thing. But you notice it has a little bit of chaos, and then it kind of comes back for a bit. And that's more pronounced in the 6th case, where it comes back in here, but I really don't know why. And let's see what else I've got here. So this next thing is, the next thing I wanted to talk about, but I do not have time to talk about, was giving the initial condition n2 to your sequence. So here was 1 through n. Now we're back to the Hofstadter recurrence, but we're giving it an n2. Here n is 5, and you get this sequence, where you get, these are not constant blocks, these alternate between 2 and constant. But then there are actually a few things in between. And I haven't yet tried to prove that this one works the way it looks, but this, you get this. 37.2 looks kind of similar, but it actually dies. So this, it still has that, like those long blocks of something alternating with 2s, but it dies. 41.2 kind of looks like 37, but I haven't shown that I haven't found that it dies yet. And then 57.2 looks like that, which I think this is actually a quasi-polynomial. After like position 3100, I think it's a quasi-polynomial with 1,400 things interleaved. Well, 1,402, but I tried to feed that to my other program from my last talk, and it yelled at me for giving it way too big of an input. If I yelled at me, I mean it ran for about an hour, and then I killed it. So if I want to prove this is actually a quasi-polynomial, I need to optimize that thing specifically for this case. But these spots are 1402 apart, so that would be the period. And then if you change those 2s to 4s, you get some other weird behavior, where if you start with 642, 4, 642, 4. So the first 4 terms are that. This is the behavior. And this is a log plot of that. This is the entire sequence. It dies. And again, this is still the Hofstadter recurrence. So most of the pictures you've seen here are the same recurrence. And if you change that 642 to 312, it looks like that, which lasts almost as long as 642. And here's a log plot of that. And it turns out that 312 is a multiple of 4, which for most multiples of 4, I can tell you what's going to happen, but I can't tell you if it's 4 times a triangular number. 312 is 4 times a triangular number, so I have no clue why. I have, like, my conjecture is that these are the hardest case, they last the longest, but they all still die. But all the other multiples of 4, I can predict when they die, but not this one, or any other multiple of a triangular number. All right, and those last plots don't really matter, so I'm just going to stop here.
Okay, Tom, definitely glad to answer questions in private. Thank you.